Let's consider universal introduction. According to our universal introduction rule, essentially what we're doing is asserting that all objects have a certain property. But how can we explain that? How can we derive the conclusion that everything has a certain property? After all, we can't realistically go out and check all of the objects that might make up a universal domain or a universe of discourse. There may be infinite things in the universe of discourse. Maybe we're talking about physical objects. So what we want to do is essentially show that some objects, just some randomly chosen object that we know nothing about, must have a certain property if our premises are true. And if we show that's the case, then we're in a position to derive the conclusion that all things have that property. After all, there was nothing special about this object that we chose just randomly. We didn't know anything about that object. So therefore, if it can be shown to have a certain property, then anything whatsoever must have that property. This is a bit like how we know that a theorem is true of any world if we have shown that it follows from no premises. If it follows from no premises, then however the world is, that thing must be true. So same thing here. If we don't know anything about an object, but we can show that that object has a certain property, then that property must hold for any object whatsoever. It must hold for all objects. So we have here our universal introduction rule. What this says is if we have some sentence phi containing some constant, let's say c, then we can substitute in the statement for all things x, or phi, if we replace c in phi with the variable x. We would justify this move using universal introduction from step M. Now, it must be the case that c does not occur in any premise or undischarged assumption. Again, we want this to be a totally random object that we know nothing special about, nothing beyond what is true of any object within our domain of discourse. And that's how we're justified in making the leap to the universal that all things must have this property. So let's look at this proof in action. Here we're given the statement that for all things, they are both C and L. And we're also told that for all things, if they are C, then it follows that they are P. And we want to demonstrate that all things must be P. Now, obviously this makes sense, but how do we show it using natural derivation? Well, what we do is, at step 3, we will give some name to some particular object in our domain. Let's call an object A. So we know then, using universal elimination, that we can assert A is C and A is L. And so that again is using universal elimination from 1. Similarly, we know that if A is C, then A is P. And that again is from universal elimination of 2. Now, at step 5, we can assert that A is C. That just follows from conjunction elimination of 3. And so at step 6, we could assert that A is P. That is conditional elimination from 4 and 5. And now, since A does not appear in either of these premises, we know nothing special about A, right? A was just a name we substituted in. And given the universal properties that hold for all objects in our domain, it had to follow in this case that A was P. So therefore, it must follow for all things in our universe of discourse that they are P. So we can assert universal X, P, X. And that will be our universal introduction rule. And all we have to cite is 6, so long as the name at step 6, A, does not appear in any premise or any undischarged assumption. So that's your universal introduction rule at work.